This is a question also based on the concept of silvered lens, something that we saw in the previous video as well. So the question goes as follows. A pin is placed 10 centimeter in front of a convex lens of focal length 20 centimeter, and it is made of glass with refractive index 1.5. The surface of the lens farthest from the pin is silvered. The radius of curvature is 22 centimeter. Determine the position of the final image. Is the image real or virtual? So this question is essentially similar to the previous question that we saw. We can just glance over the previous question that we had. So here was the previous question in which we had a plano-convex lens with a silvered plane surface, and then we decomposed this plano-convex silvered lens as a sum of three components: the lens followed by the mirror followed again by the lens, and then we used the lens formula or the reflection from a mirror to basically find the image, the final image for any object. So we subsequently use the lens formula, then reflection from the mirror, and then again the lens formula to find out the final image location. And a simpler or a faster way to solve this question we had seen was by using the concept of power of combination. So power of a combination of optical elements is sum of power of individual optical elements, and then we applied it to our combination of lens followed by mirror followed again by the lens, because the ray comes in, sees the lens, then sees the mirror, and then goes back through the lens and comes out. So we will use the same principle over here. And finally we saw that this silvered lens combination is somewhat equivalent to a concave mirror, because a concave mirror also reflects things back and then focuses in front of it. So we will use similar concept over here. So power of combination of optical elements is equal to sum of power of individual optical elements, where Pi is power of an individual optical element. So let us now draw the diagram first. So we have a convex lens which is silvered, and then a pin is placed right here. This is our object, and then we need to find out the image location. So this is the principal axis. So we can decompose our optical element as we had seen previously. So we have this optical element. So this can be broken down into a convex lens plus a concave mirror followed by the lens again. Why we did such a decomposition? Well, that's because the rays will come, they will encounter the lens, and then they will refract from the lens. Then immediately after the lens there is the mirror. I am drawing some gap just to make things look a little bit more clearer, but this thing is essentially pasted on top of the lens itself, but just to make things a little bit clearer. So from the mirror these rays will then get reflected, and then they will again encounter the lens and then get further refracted by the lens. So this is how the rays will encounter. So we have the incident white rays, they will refract first through the lens, then we have the reflected blue rays from the mirror, and then finally the rays will refract through the lens again to give us these red rays. So that's why we have first the rays will first encounter the lens, then they will hit the mirror, and then they will come back through the lens. So in this situation we would write power. Power is basically 1 over focal length. So power is defined as such, and pi is nothing but 1 over focal length of the individual elements. This is focal length of the total. So in our case we have the focal length of the combination is focal length of the lens, 1 over focal length of the lens, then 1 over focal length of the mirror, and then again the lens. Now we are given the focal length of the lens and we are given the radius of curvature. So radius of curvature determines the focal length of the mirror. So focal length of the mirror is radius of curvature divided by 2. This comes from paraxial approximation. So this gives us, this is equal to 22 centimeters divided by 2, which is 11 centimeters. And focal length of the lens we are given is 20 centimeters. So we can find out, we can put in these numbers out here. So this is 2 divided by 20 centimeters plus 1 divided by 11 centimeters. So we can simplify it. This gives us so the focal length comes out to be this is the equivalent focal length of our combination of our silvered convex lens. So we have found out the equivalent focal length. Now we need to find out the image position. So note that this combination is equivalent to having a concave mirror with equivalent focal length f, as we have just found out, which is equal to 110 centimeter over 21. So this setup is equivalent to having a concave mirror with such an equivalent focal length. Why do I say so? It's because you can see from this ray diagram, because of the presence of this convex lens and the concave mirror, the parallel rays coming would get converged in front of this combination. So this is just like having a single concave mirror. If we had, then similarly the parallel rays would have come and then they would have been converged to some point. So this is how we are drawing the parallel, drawing the equivalence. So we can use the mirror formula. One by V plus 1 by U is equal to 1 over F, and then we can plug in the values for U and F that we have just found out. So now we will use the sign convention. So since the rays are coming from the left side, all such directions move in the direction of the ray are positive, and all these directions are negative. So focal length is negative, and U is also given as 10 centimeters, so it is minus 10 centimeters according to the sign convention. Sorry, this is 1 over F, not F. So that would be 21 over 110. So let us simplify it. This gives us the image distance as negative 11 centimeters. Now, the negative sign over here in the image distance, negative sign denotes that image is in front of the combination, of the combination that we had, combination of silvered lens, which is effectively a concave mirror of some effective focal length. So thus the image is real. So let us look at the diagram to make sure it makes sense. So the image of this object, this direction is negative, so the object was here. This was our object at 10 centimeters, image is at 11 centimeters. So this is our object, somewhere here is our image. So this image is being formed in front, meaning on this side of this combination that we have. So that means it is real. Had it been formed somewhere over here, somewhere behind the silvered part, then it would have been virtual. So this solves the question. We found the image distance and whether the image is real or not. So our image is real.